Hello friends, in the previous lectures we discussed about radiative characteristic of plane surfaces and their properties and their evaluation from basic fundamental laws. Now in this lecture we will discuss about radiative transfer between two surfaces. The first topic on this series is based on view factor. So it is pretty much very much clear that amount of energy exchanged from one surface to another will depend on orientation of the two surfaces. So for example, we have two surfaces having the same area and similar temperatures. If their orientation is not same, the amount of energy transferred from one surface to the other will not be same. For example, if we have surface 1 and surface 2 in this configuration having the same temperature and area, and we have this configuration, the two plates have the same area, similar temperatures, but the amount of energy transferred between these two surfaces will not be same, and the reason is that the orientation of one surface with respect to other is different. Now to account for this effect, the angular dependence or the orientation, we talk about view factors. Now on view factors, we talk about exchange of radiative energy between two surfaces bounded by transparent medium. So the condition for calculating the view factor is that the medium surrounding these two surfaces should be vacuum. We can also calculate similar factors when the medium is not surrounded by vacuum or it is surrounded by some kind of gases that absorb and emit radiation, but that part we will reserve for later lectures. In this part we will assume that the surfaces are surrounded by vacuum, and we also assume any absence of participating medium. The second assumption in this evaluation of view factor is that the surfaces are diffuse, that means they emit radiation equally in all the directions. They also reflect radiation, they may or may not reflect radiation, but if they do, they reflect it in diffuse manner. So view factor is basically the orientation between the two surfaces. Sometimes it is called configuration factor, angle factor or shape factor. So we define this view factor as energy leaving one surface and striking directly to other surface. So what we mean by directly striking the other surface means that reflected radiation from some other intermediate surfaces is not accounted. So view factor means that radiation is emitted by one surface, it is diffused and it is absorbed by the other surface directly. There is no intermediate reflection that is taken into account in the evaluation of view factors. So the definition of view factors goes like this: for two surfaces AI and AJ, let us consider some infinitesimal areas dAI on surface AI and dAJ on surface AJ. The view factor between these two infinitesimal surfaces is defined as diffuse energy leaving surface dAI directly towards and intercepted by surface dAJ divided by total diffuse energy leaving surface dAI. So total energy will be leaving surface dAI in all 2 pi solid angle, but only a fraction of this energy will actually reach surface dAJ, and this is governed by the orientation, the solid angles and relative areas of the two surfaces. So how do we evaluate this view factor mathematically? So review factors basically gives you an idea how much rate of heat transfer actually taking place between surface AI or first surface and surface AJ, the second surface. So although the definition of view factor is equally applicable when the surfaces are gray, that means their emittance and absorptance does not depend on wavelength, but in this particular derivation we will assume that the surfaces are black, that means they emit radiation equal to the black body radiation and they absorb all the radiation falling onto the So, the view factor definition that we will derive will be based on the black body radiation. However, the view factors are applicable to gray surfaces as well. So, energy leaving surface AI and travelling to surface AJ is calculated based on the intensity of radiation of black body IB. So, the amount of energy emitted, total amount of energy emitted by surface AI depends on the black body intensity IB, which is we know is energy transmitted or emitted per unit solid angle per unit area normal to the rays. So, we have to multiply by the projected area dAI cos theta I to calculate the total energy and multiply by solid angle between surfaces I and j, that is d omega ij. We can write the value of solid angle as IB cos theta j dAI dj upon s square. So, what we have done is we have written the solid angle in terms of angle theta j. So, d omega ij is basically given by cos theta j dAj upon s square, that is the projected area along the direction Sij. Sij is the direction joining surface AI and surface AJ. So, along this direction the projected area of dAj is dAj cos theta j, and then divided by the distance between the two surfaces s square gives you the amount of energy leaving surface dAI and reaching surface j. So, the view factor is basically defined as amount of energy that is emitted and received by surface j divided by total amount of energy emitted by surface AI. So, total amount of energy emitted is equal to pi times IB dAI. This is the total amount of energy that is emitted by surface AI dAI, and then we divide the amount of energy received by surface AJ dAj with by this total amount of energy emitted, we get the view factor between these two infinitesimal surfaces, that is dF, the small view factor between surface dAI and dAj is equal to cos theta I cos theta j divided by pi s square dAj. We can also write this view factor in terms of vector notation, where we have the angle cos theta I written in terms of the normal vector Ni. Ni is the normal vector at surface AI dotted with the vector joining the two surfaces Sij divided by the magnitude of this vector Sij. This is the angle cos theta I. So, we replace the cos theta I and cos theta j with this vector quantities, and we get the value of view factor as Ni dot Sij times Nj dot Sij divided by pi s power 4 into dAj. So, we can sometimes use vector notation to evaluate the view factors, or sometimes we can use the trigonometric angles to calculate the view factors. Now, the view factors evaluated from one surface to another, that is surface 1 to 2 dF dA1 to dA2 can be used to evaluate the view factor from surface A2 to surface A1, that is dF A2 to dA1. So, we have to basically apply what we call reciprocity theorem. In reciprocity theorem, the view factors from surface 1 to 2 is related to surface 2 to 1 using their areas. So, what we do is, in the previous definition of view factor dF dAI dAj, we multiply by the area of the surface dAI, that is we multiply by this area, and what we get is expression of view factor multiplied by the small element area dAI, and this expression is symmetric in I and j. So, if we replace I with j and j with I, this expression will not change. So, what we conclude from this expression is that dAj dF dAj dAI, that is view factor multiplied by area of surface j is equal to area of surface AI, small element area dAI, times small view factor from surface AI to surface j. That is the reciprocity theorem. Okay. So, if you know view factor from one surface to the other, you can calculate easily the view factor from the other surface to the first surface using this reciprocity theorem. Now, so that this exercise was done to calculate view factor between two infinitesimal surfaces dAi and dAj. We can extend the same logic to find out view factors between a small infinitesimal surface and a finite area surface. Okay. So, if we want to find out the surface area or this view factor, that is view factor from a small infinitesimal surface dAi with whole surface Aj, we have to basically extend the same logic. The total energy leaving surface dAi towards the entire area Aj. So, all we have to do is use the previous expression that we basically used. We used this expression Ib dAi cos theta I d omega ij and just multiply or integrate over the entire area dAj. So, this basically gives you the total energy leaving dAi towards all of Aj. So, all we are doing is just integrating over the area Aj, and we define view factor again by dividing this as energy with total energy. So, this is energy reaching surface, the entire surface Aj divided by total energy emitted, that is pi times Ib times dAi. Okay. So, we just divide by the total amount of energy emitted by surface Ai, and we define this as a view factor f dAi Aj, and this view factor expression of this view factor is very similar to the previous one, just we have an integration here over the entire surface Aj. So, the expression is integration over the entire surface Aj cos theta I cos theta j upon pi s square dAj. Now, again this will satisfy the reciprocity theorem that we discussed. So, df, we write df from the entire area Aj to small area dAi is equal to the amount of energy emitted from the surface, okay, and integrated over the entire surface Aj. So, the first quantity is basically the amount of energy emitted from surface j, total surface j reaching surface element, small surface element Ai, and then we just integrate over the entire surface, okay, and divided by the total energy pi Ib dAi, and then the view factor df Aj over dAi, this Ai is constant over Aj, the dAi is not changing, we can take it out, okay, and this quantity becomes pi times Ib, the Aj becomes in the denominator. So, we get df Aj to dAi, that is the view factor from the entire surface Aj to small element dAi is equal to the area of small element dAi, which we have taken out from this integral divided by Aj from here, integrated over this quantity cos theta I cos theta j upon pi s square dAj, okay. And what we identify from this is this quantity is basically the view factor that we derived this one previously. So, what we get is this reciprocity theorem, the total area of surface j Aj multiplied by the view factor from the entire surface j to small element dAi is equal to the small area of surface Ai and view factor from small element Ai to the entire surface Aj. So, this satisfies the reciprocity theorem. Now, just like the view factors between an infinitesimal area and a finite area, we can calculate view factor between two areas of finite magnitude. Now, in the case where we calculated view factor between an infinitesimal area, we just integrated over area dAj. Now, when we are trying to find out view factors between two finite areas, we have to do double integration, and this double integration has to be taken place over the entire surface Ai and surface Aj. So, the total energy emitted from surface Ai is Ib times cos theta I dAi, and this surface energy basically reaches the surface Aj, okay. So, this is the total amount of energy between surface Ai and surface Aj. Now, we should keep in mind that the temperature of this surface should be uniform. Okay. If the temperature of the surface is not uniform, the intensity IB will vary over the surface, and then the definition of view factor will change. For this purpose, we will assume that IB is independent of the surface, okay, that is it is uniform over the surface. So, this total amount of energy, when we divide by total energy emitted by surface AI in all the solid angles, that is pi times IB times AI. So, this is the total amount of energy emitted by surface AI over all the solid angles. We divide this total energy reaching surface AJ by this quantity, we get the definition of the view factor F AI AJ, which is equal to, now this AI will basically come in the denominator, and the pi will basically come in the denominator of the expression of the energy reaching AJ. So, the view factor is basically F AI AJ is equal to 1 upon AI cos theta I cos theta j upon pi s square and double integration dAj dAi. So, this is the view factor between two finite surfaces. Now, this expression the AI times F AI AJ is symmetric. Okay. This expression is symmetric, that is when we change the I and j indices, the expression does not change. So, from this we can conclude that AI times F AI AJ is equal to AJ F AJ times F AJ AI. So, that is the reciprocity theorem is valid for view factors on finite areas as well. So, other than these reciprocity theorem, we also have summation rule. So, if we take an enclosure of any number of surfaces, okay, the total amount of energy leaving any surface I including itself, okay. So, the total amount of energy leaving surface I and going to all the surfaces including itself should satisfy the conservation of radiative energy, okay. And we can basically based on this argument conclude that the summation of view factors over all the surfaces j is equal to 1 to n will be equal to 1. That means, total amount of radiative energy is conserved, okay. So, all the energy leaving surface I should reach one of the surfaces from 1 to n, and the summation over the view factor should be equal to 1. So, what is basically view factor? View factor is nothing but a fraction of how much energy leaving surface 1 is reaching to other surfaces. So, this basically gives you an idea of that the fraction should add up to 1. Based on the same thing, same argument, the flat or convex surface will have a view factor of 0 to itself. That means, if you have a flat surface, the energy will be emitted in all direction and this energy will not strike itself, the surface will not receive any radiation that is emitted by itself, okay, because it is flat. And similar argument, the convex surface also will not receive any radiation falling onto itself, okay. So, for these two surfaces, the view factor Fii, that means the view factor to itself will be equal to 0. On the other hand, for concave surfaces, the view factor will not be equal to 0, it will have some finite value, because some amount of radiation leaving this surface will actually fall upon this surface itself, okay. So, Fii for concave surfaces will be greater than 0. Now, so these are the definition of view factors between infinitesimal area and a finite area, and between two finite areas. Now, how do we evaluate these view factors? So, there are number of ways by which these view factors can be evaluated. We can do double integration, that is called analytical method. There are simplified methods like contour integration, which basically simplifies the double integration, double surface integral into line integral, the path integral. Then we have Hotel cross string method, inside sphere method. We can use numerical methods where we divide the surface into a small number of infinitesimal surfaces, and we can do calculation based on some numerical scheme. And then Monte Carlo method can also be used. Monte Carlo method based on the ray tracing scheme can also be used to evaluate the view factor. So, in this lecture I will focus on the analytical methods. So, we have the first method, the first analytical method is the area integration, where we have to basically integrate over the surfaces to evaluate the view factor. So, we have already defined f a I a j as equal to 1 upon a I and then double integral cos theta I cos theta j. So, this was the expression we already developed for the view factor f I a j between two finite surfaces. Now, to evaluate this integral, we use Cartesian notation. For different problems we can use different notations, but just to give an idea, in the Cartesian notation we can represent any point on the surface, any point on the surface. First we have to find out the origin. We can put an origin on the surface, okay, and then we can represent any vector r either on this surface or on the other surface from this origin, will depend on the x coordinate, y coordinate and z coordinate of the surface, okay. And we represent the vector Sij as the vector joining 2 points or 2 infinitesimal areas between two surfaces. So, this is Sij, and Sij can be represented in terms of the coordinates of this point, which is Ri, and coordinate of this point, which is Rj. So, Sij is equal to Rj minus Ri, and the view factor and the direction Sji is just with a minus sign, okay. So, but ultimately what we are doing is taking the vector difference between the two coordinates, and this can be written as xj minus xi, the I vector, yj minus yi and zj minus zi, okay. So, other than this we also need the information for angles. So, let us say we have been given the normal vector to the two surfaces represented by the direction cosines L, M and J. So, L is the direction cosine in x direction, M is direction cosine in y direction and N is direction cosine in z direction. So, n cap is the normal vector. So, in the sense Ni will be normal vector to surface I and Nj will be normal vector, unit normal vector to surface j, okay. And we can find out cos theta I and cos theta j using this expression, okay. So, this is the information that we need to find out the view factor using this analytical method. So, of course, this method is going to be little involved, as we will see with the help of an example. There is going to be lot of mathematics, we have to take care of lot of vector quantities. To simplify this method, although this is not always the simplification, for some geometries you will find that contour integration is a little easy to do, while for some quantities, for some configuration actually the contour integral may be more complicated than the area integration, but for some applications this will be easy. So, contour integration is based on Stokes theorem, that basically converts a surface integral into a line integral. So, the Stokes theorem is given by this. So, let us say we have f, a function, a vector function which is defined on surface A, including the boundary gamma, okay. So, there is a function f. The Stokes theorem says that the surface integral of the curl of f and area dotted with the area vector and integrated over the surface is equal to the function f evaluated using the line integral over the path around the surface. So, if you have this surface A, this is the path that we have to follow, okay. So, this is basically the boundary of the surface. So, we have surface A and we have this path of this around this surface that we have to evaluate, okay, and n is the unit normal vector to the surface, okay. So, with some mathematical manipulation, the surface integral, the double surface integral in the finite area view factor can be converted into double line integral by applying the Stokes theorem twice, and what we get is a1 f12, that is basically the view factor between surface 1 and 2 or I and j, as equal to 1 upon 2 pi double line integral over the two contours, that means contour of surface 1 and contour of surface 2, and the integrand here is ln s. S is the same Sij, the magnitude of Sij is basically the S, okay. So, this is how we will evaluate. So, let us conclude this chapter with one example. So, we have two parallel plates. The width of each plate is W, and the distance between the vertical distance or the separation between the two plates is H, and the plates extend to infinity. That means the thickness of these plates in the plane of the board or paper is infinity. So, we have to evaluate the view factor for this configuration. So, let us apply the area integration method for this. Okay. So, we have this is surface A2 and this is surface A1, and any point we can just put our coordinate system here. This will be y direction and z direction will basically be in the plane of the paper. So, we will start with the z and then we can put z tending to infinity for the thickness of the plates reaching infinity in the z direction. Okay. So, this will be Sij. Okay. So, this will be x1 and the coordinate of this point will be x2, and similarly y1 and y2. So, what we write is the first thing we will write is the angles cos theta 1. Okay. This is the angle theta 1. So, cos theta 1 is simply equal to and this will be h by s. Okay. So, cos theta 1 will be equal to h by s. Okay. So, where h is basically the distance. So, from this triangle h by s, Sij is simply equal to s, h by s is equal to cos theta 1, and this will also be equal to cos theta 2. Cos theta 2 and cos theta 1 are equal in this case, but in this particular example. So, we write s is square is equal to x2 minus x1 square, already defined x2 and x1, plus h square plus z2 minus z1 square. Now, we are assuming that the plates are of finite depth, but we will eventually put z tending to infinity. So, we define first a view factor, a small element dA1 to entire surface A2. Okay. So, first we will define, we will take a small element on surface A1 and define the view factor from this small element to the entire surface A2, and this will be equal to, again we will use the expression that we have already defined. Let me just quickly show you the expression. So, this expression we are going to use for the view factor, f dAi aj is equal to cos theta I cos theta j pi s square dAj. Okay. So, this expression we are going to use. So, this can be defined as where z limits are from infinity to infinity, we assume that the z direction is infinite. We have to integrate over the two areas, and then in the denominator we have So, remember we have s power 4 in this, because s square is already there in the expression, but we have s in cos theta also. So, in the denominator we end up with s power 4. Okay. So, we can evaluate this, h square is constant, can be taken out upon pi. Okay. First we can integrate with respect to, so this is going to be dx, okay. So, this is dx1 dz dx2. So, dx1 is basically in the direction of x direction, okay, and dx2 we can just replace it with dz, otherwise it will confuse you. So, we will just write dz here. We first integrate with respect to z and then we will integrate with respect to x. So, this will give you pi by 2 0 to w dx upon x2 minus x1 square plus h square power 3 by 2. Okay. And then we will write h square upon 2 okay, and we can use the integration rules by change of variables, and then this will be simply equal to w minus x 1 upon w minus x 1 square plus h square plus x 1 square plus h square. Okay. So, this is the view factor between small area dA on surface 1 and entire surface A2. Now, to calculate the view factor from entire surface A1 to A2, we just have to integrate over the entire surface A1. So, this will be 1 upon W integral 0 to W f of d A1 A2, and then we just integrate over dx. So, for the entire surface A1 we are just going to integrate. So, we substitute the value of f dA1 A2 from the previous expression, we get 1 upon W 0 to W minus x 1 upon root W minus x 1 square plus h square, and then similarly 0 to W x 1 dx x 1 square plus h square. Okay. So, these two integrals again can be solved easily. Also it is worth observing here that the two integrals are pretty much the same. Okay. We can change of variables, they will be same. Okay. So, so what we basically get here is so there should be a 2 here. Okay. So, we get f A1 to A2 as equal to the two integrals are pretty much same as I said. So, 0 to infinity x dx root x square plus h square, where we have used x is equal to w minus x 1. Okay. With the change of variables you will find that they are basically the two integrals are the same, and we can just take twice of them, and this will be equal to 1 upon w root x square plus h square 0 to w, and this will be equal to 1 plus h square upon w square minus h upon w. So, this is the view factor basically. Okay. So, f 1 to 2 for this configuration using the area integration technique is simply 1 plus h square minus h, where h is equal to h by w. Okay. So, this is how you can apply the area integration technique and find out the view factors. As you have already observed, the mathematics involved in this calculation is pretty involved, and many people, many researchers have already found the view factors for standard configuration, and they are available at the back of the textbook. Okay. So, please try to solve a couple of configuration yourself using this method. Thank you for your time. In the next class we will use another method to find out the view factor.